Hello, welcome to my video series of data structures. This is part 1 of Module 8, the graph data structure. In this video, we will introduce the basic concepts of graph. We will use a real example to illustrate the usefulness of graph data structure. Imagine that you are a mail carrier, responsible for delivering mails to multiple addresses across the city. To organize your route efficiently, you decide to draw a map of the city, marking each destination and the roads connecting them. Let's begin by representing each location as a node in the graph. For example, each dot shown here corresponds to a location you need to visit. Nodes are also referred to as vertices, and these two terms can be used interchangeably. In the graph data structure, nodes are the fundamental data elements whose relationships you want to model. The set of all nodes in a graph is typically denoted by V. After recording each location on the map, the next step is to represent the roads between these locations as edges in your graph. For example, if there is a road connecting house A and school B, you would draw an edge between these two nodes. In graph data structures, edges represent the relationship between pairs of nodes. The set of all edges in a graph is typically denoted by E. Together, the set of nodes V and the set of edges E form a graph. We typically denote such a graph G equals VE. Sometimes, you may need to focus on only a subset of nodes in a graph. For example, a mail carrier might be responsible for deliveries in just one subregion of the city. The subset of nodes and the edges connecting them form a subgraph of the original graph. In the illustration, the red nodes and edges represent a subgraph of the complete graph. Up to this point, we have not considered the direction of the roads. When connecting two locations, we assume the road is bidirectional, meaning you can travel freely in both directions. These edges, which do not have a direction, are called undirected edges. Graphs made up of nodes and undirected edges are called undirected graphs. However, some cities have one-way roads. In these cases, we need to specify the direction of each edge to reflect the one-way nature. For example, in the illustration here, arrows indicate the direction of travel for each edge. Edges with direction are called directed edges. A directed edge is unidirectional, meaning you can only travel from the beginning of the arrow to its end. For example, you can go from apartment C to school B, but not the other way around. The node at the start of the arrow is called the source node, while the node at the end is called the target node. In this example, apartment C is the source node, and school B is the target node. A graph formed by nodes and directed edges is called a directed graph. We can estimate a location's accessibility by counting the roads that begin at it and those that end at it. For example, apartment C is connected to many roads in the city, making it highly accessible. The total number of edges connected to a node is called its degree. In this example, apartment C has a degree of 7, while store E has a degree of 3. In a directed graph, it is often useful to distinguish between the edges entering a node and those leaving it. The number of edges that enter a node is called its in degree, while the number of edges that leave a node is called its out degree. For example, apartment C has an in degree of 3 and an out degree of 4. Some locations in the city can be highly accessible, connecting to many roads. The corresponding nodes in the graph therefore have high degrees. Specifically, if a node is connected to every other node in the graph, its degree is v minus 1, where v represents the total number of nodes. In other words, such nodes have degrees on the order of OV. On the other hand, some nodes are only connected to a few others, making their degrees on the order of O1. If a graph is dominated by high-degree nodes, the total number of edges can grow on the order of OV squared. This is because the graph contains V nodes, and each node's degree is on the order of OV. Such a graph is called a dense graph. On the other hand, if the graph is dominated by low-degree nodes, the size of its edge set is on the order of OV. This type of graph is known as a sparse graph, and most real-world graphs fall into this category. To more accurately estimate travel time, we need to record any delays associated with both deliveries and driving. For example, you might spend 5 minutes at apartment C searching for the correct room number. Similarly, the drive from apartment C to hotel D could take 30 minutes. Such quantitative attributes associated with nodes or edges are called weights. Weights assigned to nodes are called node weights or vertex weights, while those assigned to edges are called edge weights. In our example, the node weights are shown within the nodes, and the edge weights are marked beside the edges. Graphs without node or edge weights are called unweighted graphs. Graphs that include weights on the nodes are known as node-weighted graphs, and those with weights on edges are called edge-weighted graphs. In general, both are classified as weighted graphs. However, in most contexts, the term weighted graph typically refers to an edge-weighted graph unless otherwise specified. Now that we have both node and edge weights, we can estimate the time needed for any trip. A trip typically involves a series of locations to visit and the roads connecting them. For example, the trip from Hotel D to Store E is highlighted in red in the graph shown here. Formally, a trip can be defined as an ordered list of nodes V1, V2, all the way through Vk. For each pair of adjacent nodes, Vi and Vi plus 1 in the list, there is an edge that goes from Vi to Vi plus 1. This sequence of nodes and edges forms a path in the graph. For example, the path shown in the graph consists of nodes Hotel D, Apartment C, store E, and the two red edges connecting them. Among the nodes V1, V2, all the way through Vk, if no two nodes in the sequence are the same, the corresponding path is called a simple path. On the other hand, if the first node V1 is the same as the last node Vk, the path is called a cycle. For example, the nodes Hotel D, Apartment C, Store E, and Hotel D, along with the red edges, form a cycle in the graph shown here. Graphs that contain at least one cycle are called cyclic graphs. Conversely, graphs that do not contain any cycle are called acyclic graphs. Now, consider the red path highlighted in the graph. We can estimate the time required for this trip by summing the node weights and edge weights along the path. The total sum is called the length of the path. For example, the length of the path shown here in the graph is 108. When calculating the length of a path in an unweighted graph, we assume all node weights are 0 and all edge weights are 1. Under this assumption, the length of a path in an unweighted graph equals the number of edges it contains. For example, if the graph shown here were unweighted, the red path would have a length of 2. To find out whether you can travel from one location to another, you must check if a path exists between them. In a graph, if there is a path from one node to another, those nodes are considered connected. When every node in a set is connected to every other node in the same set, that set of nodes forms a connected component of the graph. In a directed graph, two nodes are considered strongly connected if each node can be reached from the other. For example, if there's a path from house A to apartment C, and another path from apartment C back to house A, then house A and apartment C are strongly connected. Note that in directed graphs, two nodes may be connected without being strongly connected. Similarly, in a directed graph, a set of nodes that are all mutually strongly connected is called a strongly connected component. In this video, we introduced the fundamental concept of graphs. We began by defining nodes and edges, noting that edges can be either directed or undirected. We then discussed how to measure a node's connectivity through its degree. We explained that dense graphs tend to have many edges, whose edge set size is on the order of OV squared, whereas sparse graphs have relatively fewer edges, whose edge set size is on the order of OV. We also showed that weights can be assigned to nodes and edges to represent additional information, such as travel time. To determine whether two nodes are connected, we look for paths between them. We can estimate the cost of traveling along any given path by calculating its length. Finally, we introduced the concept of a connected component, a set of nodes that are all reachable from one another. In the next video, we will discuss how to implement the graph data structure. Thank you for watching, and see you next time.